also particularly want to discuss or brainstorm about how we should think about it conceptually, architecturally, sort of going forward for more complex tasks. So deep learning, of course, has made amazing strides on several engineering applications. On speech recognition, we today have a below 5% word error rate. On ImageNet dataset, we have an under.
Sorry.
Sorry, that was me.
That was Gagan, not me. So.
On ImageNet, we have under 5% error. But still, there are several complex tasks where we are far from perfect, like true natural language understanding, the way we have conversations with each other, or even logic. There is almost no good understanding of how to put logic into deep learning. Now, deep learning works well, but do we really understand why it works? Specifically, what are the exact limits of deep learning? Do we understand what class of real-world functions deep learning can learn? Can we say that these are the type of functions that it will learn, and these are the types it will not learn? And are there any specific properties about real-world functions that make them learnable using deep learning? And note that I'm specifically talking about learnability, not just representation. We all know that deep networks, as long as they have nonlinearity, can represent any function, any computable function. But here we're talking about learnability. That means, given training data set, I should be able to learn it using the gradient descent.
Do you care about efficiency or no?
Yes. I mean, here I'm talking about just even polynomial time learnable is good enough, just whether you can learn it or not. And I want to suggest that instead of just focusing on real engineering data sets, it is also beneficial to look at synthetic data sets to understand this conceptually. And synthetic data sets means that the training data is obtained from some mathematical function. And there is a good reason to do this, because when I give you a real data set and you get some loss, let's say it's correctly classifying 80% of the case, you don't know whether it has fully learned the function to the best possible level because you don't know what is the optimal point. And with synthetic data sets, you have this advantage that you know what the ground truth is. So if you know that the model generating the data set is small, then you know it can be learned to zero error using some model. So you can easily test how well this learning technique, or any learning technique for that matter, does on synthetic mathematical class functions. So here are some good possible mathematical function classes. A good one for nonlinear functions is polynomials. Okay? This is the classic one for representing nonlinear functions. You can also have decision trees, and you can ask, can deep learning learn all decision trees of limited size? You can also ask functions that are generated using teacher deep networks. So you could just have a fixed synthetic network, small one, and you can have input-output pairs from that. But you don't know the black box. The network is a black box. You can ask whether now deep learning can learn this. And particularly interesting is the real-world functions. In which synthetic class of these does it fall? Are there some specific properties, mathematical properties that these real-world functions have that come from one of these classes that makes it more learnable? So that will be the first part of the talk. In the second part, I will make it much more open-ended. And we will get into questions like, what should we architecturally, what the current deep learning framework that you have, is it sufficient? Or are some major architectural changes required to handle more complex cognitive tasks like natural language understanding or logic? And particularly, I'll try to argue that we need some bigger level changes, like we need to have a more modular view of deep learning, and we need to have good memory support in addition to a deep network. So this part will be more speculative, and if time permits, I hope we can have a discussion or brainstorm about what do you think are the right ways to extend this architecture. And the main points that I try to convey is that here are some of the theoretical results. Okay, first, from the function classes of polynomials, we will argue that we will prove that polynomials can be learned using deep learning. Then we'll go to learning teacher networks. We'll show that very shallow teacher networks of depth 2 or 3, especially depth 2, can provably be learned using deep learning with some assumptions. But then, on the other hand, we'll argue that very deep random networks, you have to take a random teacher network and make it very deep, then somehow it's very hard to learn those. In fact, they might even become cryptographically hard to learn. And I'll show evidence for that. I'll also give some evidence to show that if your network has some modular structure, that means it can be broken down into pieces which thin connections, then that actually helps it in making more learnable. And finally, we will explore possibilities of adding memory and modular structure to the deep learning architecture.
So when you say easy to learn, are you going to allow the learner network to have depth somewhat more than the teacher network?
Yeah, I'm allowing it to have more. I'll give you results saying that sometimes it may not even be necessary.
Okay.
So let's go through the basic deep learning framework. You have some unknown function, and you just have input-output pairs from that function. The inputs to be drawn from distribution, maybe some from real-world distribution, so that you can predict its value on some new inputs that you will see in the future. And this is exactly like linear regression, where you have some data points that try to fit a line to it. But instead of just fitting a line, we want to fit a higher dimensional curve, which is given by a nonlinear function. And one way to get a nonlinear function is to have a deep network with a nonlinear activation. And if you make this deep enough, you can actually represent any function, which of course doesn't mean that you can learn any function. So you are given input-output pairs, and you train the weights of these to optimally match the input-output pairs. And the way you train it usually is you look for a given set of weights, you check whether it agrees with the function, the training function, and you minimize, say, the square loss. So this is your loss. And then you take the gradient of the loss with respect to the parameters, and you keep shifting, moving the weights so that the loss decreases. And you hope that in the end, it will match the function, at least in most of the input-output pairs. Now, this is good if the loss surface is convex. If the loss surface is convex, you're guaranteed to reach the minimum point. But in real world, and especially in deep learning, it's easy to prove that the loss surface is not convex, because there are many, many minimas, and you don't know whether every minima is equally good as the global minimum. So why does this work in engineering applications? It has also been found that in real networks, as you go up, you are learning more and more complex concepts. So at the on image, this is a network for analyzing images. At the very lowest layer, you understand things like lines and curves or edges. And then as you go up, you find complex shapes. And then at a very high level, you might find things like face of a person or a face of a cat. And it's also found, there's some evidence to show that the outputs get sparser as you go up higher, because you're finding less and less complex phenomena in a piece of input. So as I said, it works well, but we would like to understand conceptually why it works well and when it would not work well. Let me point to some related work. This is a very limited set of related work. So in terms of non-convex optimization, minimizing non-convex optimization, there are statistical physicists who have argued that the loss surface for deep learning actually might have many local minimas, but most of the local minimas have values very close to the global minimum. And they arrive at that by modeling the loss surface as some kind of a Gaussian random process. There is other works which explain why SGD, specifically the stochastic aspect of the gradient descent, helps in escaping saddle points. So even though saddle points for gradient descent is problematic, for stochastic gradient descent, actually it can escape. In terms of learnability of feature networks, there are several results which talk about why two-layer teacher networks, ReLU networks, can be learned by two-layer student networks. In terms of overall conceptual view of deep learning, Michael Elaz has a theory that deep learning, the layers are nothing but doing dictionary learning on top of each other iteratively. So you go from a dictionary or a big dictionary of atoms, you learn the lowest level concepts, and then you go to another layer of dictionary learning, get high level concepts, and so on and so forth. Modular architectures have been proposed. There's something called capsules, which was proposed by Hinton, and recently Papadimitro and some of his colleagues have argued how in deep networks in the brain you might have the notion of pointers, something called assembly pointers. Pointers can point to complex objects. So here are some of the exact results we will go over. So we'll start off with just linear decomposition, just a linear non-convex convex problem, which is low rank approximation, where you're trying to express a matrix as a product of two thin matrices, and this is non-convex. And it is proven that if you apply gradient descent on this problem to minimize the error, Frobenius norm of the error, then there cannot be any bad local minimas. I mean, there are many minimas, but they're all global. And this has been extended to deep learning deep linear networks. Then we will go to nonlinear functions. We will show that polynomials can be learned by using networks of depth 2, where the size of the network depends on the degree of the polynomial. And then from there, we will go to higher depth networks. We'll show that the learnability of such a teacher network actually drops exponentially in the depth. And as the height edge increases, this actually becomes more like a cryptographic hash function. We won't prove that exactly, but we'll give some evidence to that effect. And finally, we will get into modularity structures, and we will argue that if the network is modular, then you can do something to it to actually make it learnable. Any questions? Feel free to interrupt me at any time. Any discussion points, vague ideas?
Can you explain the footnote?
Oh, yes, before I switch, good point. Yeah. So we will not assume here that the input data distribution in these teacher networks or for the polynomials is adversarial. If you assume that the inputs are adversarial, then in fact the problem is NP-hard, even for learning a one-layer network. Okay. So we will assume a more benign distribution, specifically maybe a Gaussian distribution. Yes?
What's the definition of learnability?
Well, broadly, it is that you want to learn the function at least up to 1 minus epsilon accuracy, or let's say even if you get 90%. Let's say if it's a binary function, if you can get to 90% accuracy, that's you're doing something non-trivial, and in polynomial time.
And this is assuming the same Gaussian input distribution.
Yes.
Okay.
For polynomials, what is the dependence on the degree?
It's exponential in the degree. It actually drops with the sparsity. So if the degree is high, but the number of terms is small, then
What is exponential in the degree? The size
of the student
network. Okay.
So let's start off with just simple non-convex problem of linear decomposition, where let's say you have a Netflix ratings movie, you have users here, movies here, and we believe that this can be represented by using a latent product of two latent matrices, thin matrices. Let's say the movies belong to some topic, users are interested in certain topics. And the question is now, if you try to recover these by using gradient descent, by minimizing the error difference between these two, then will you converge to the right, the right decomposition? And this is basically usually done by using SVD if the matrix is full. What can be proven is that just TensorFlow like gradient descent will also not get stuck in any local minimum outside of this optimal decomposition, which is quite surprising. It was only recently shown. And this can be viewed as a result in deep learning because this product of two matrices is exactly a two-layer network, except that it's linear. It is just a product of these two matrices. There's no non-linearity here. And so you're basically giving different inputs, user, movie, ratings here, and you want to match it based on the product of these two matrices. Now, this also generalizes to deep linear network. That means even if the student network is linear, no matter what architecture it has, you will not get stuck in a suboptimal local minimum. But linear networks can only express linear functions. This is not very useful for learning real-world functions. So let's go to learning polynomials, which is a classic way of expressing nonlinear functions. So you're just trying to learn some simple polynomial function, let's say a simple function of degree 2. So what we show is that a degree d function polynomial can be learned using n to the power d-sized two-layer network, where n is the number of variables. And in fact, you can even reduce the size of the student network if you assume that the polynomial is sparse. That we don't have full proof, but we have some mild evidence for that. And the reason why you can learn a polynomial is actually very simple, using a two-layer network. Let's think about a polynomial of, the basic point is that a polynomial of degree t can be viewed on n variables, can be viewed as a vector over n to the power d dimensions, because you get one monomial for each as one of the basis vectors. So you can express it as a vector over these basis directions. So if you just have a quadratic function, if you just have a degree 2 function over two variables, unless it's homogeneous for simplification, and you just have these three basis elements, and any polynomial can be expressed as a linear combination of these. And for simplicity, if you think that the activation is quadratic, then basically you get, for each hidden unit, you get a different quadratic function. And as long as this lower layer is random, these are going to be fairly independent. So as long as you get more than three of these, you can prove that you can express a linear combination, any quadratic function as a linear combination of these. Which means that if you keep this random and you just train these upper layers, and if you assume that this is a sum instead of a nonlinearity, it's easy to see that you can learn any degree 2 function, as long as you just have 3 of these here.
So what did you say about the nonlinearity on the top?
Yeah, I made a simplifying assumption that it is linear. Yeah, but experimentally you can see that even if you make it a nonlinear, like you could take the sine, so sine will become a ball, right? You can learn these things pretty well.
But learning with linearity is actually a stronger result, right? That you don't even need nonlinearity at the top.
No, it's well, it's stronger in that sense. But if you try to learn thresholded polynomials, then it's weaker. If you want to learn region, and you can actually argue that you don't need to freeze this part. You can train this as well, and still you learn this. So this is okay, but
if the 2 inputs were, the green layer can be a linear function of the underlying thing. That means it will be just a renaming of variables.
rotation, yeah, be simple rotation.
Under some transformation.
Yeah.
Right. Okay.
But you need to have enough capacity to represent the monomials, I guess.
Yeah, so as long as you have more than n to the power d of these, you've got each monomial. Exactly. The surprising thing is, if the number of monomials, the possible number of monomials is hundreds, but you just have 3 sparse things, right? It turns out that you don't need hundreds of nodes. Somehow they adapt. If you empirically try to find it out, try to learn, let's say you try to learn, I don't know, x to the power 5 plus y to the power 5. Okay. Now over 2 inputs you can have 5 choose 2 or whatever, 2 to 5 possible things. But if you just have small number of things here, somehow it adapts to the right monomials.
So there are no cancellations happening inside the network. It pretty much finds some.
No, the cancellations can happen here when you add up.
In principle, they can, but in practice, it seems like they.
No, I don't. I'm not claiming that it's 1-to-1. Somehow you're learning one monomial at a time. Or learn the right combination so that they cancel out in the right way, and then you.
What if the labels are approximately a polynomial?
Yeah, so we tried with random. If you have random noise, then everything is
Fine.
pretty much the same argument. Quite trivially, actually. If you see mathematically, things will, all correlations will. Gradient descent doesn't change that much if you have random noise. But adversarial, it's okay. It's a harder argument.
Okay, so what is the dependence on the degree?
The number of things here has to be n to the power d. But it can also be smaller if your polynomial is sparse. If your polynomial is sparse, it's probably just proportional to the sparsity.
Not squared or something like that, just exactly equal to sparsity.
No, I wouldn't say it's exactly sparse. I don't have a proof of how it depends on sparsity. I can prove that if it depends on only k out of the n variables, then you need only k to the power d.
Oh, it's like
That's one thing you can
that
prove.
sort of thing.
And also empirically you can see that if it's sparse S, then you can turns out that you don't need too much.
Is there a simple information theoretic argument that says that number of nodes that's proportional to the sparsity is enough to capture?
To capture, yeah.
It is, right?
That's
Yeah.
Representation should be
Representation.
should be easier. Yeah.
So this is good, but it gets too wide for high degree, and to represent any complex function, you really need high degree. And that's why it's important to look at representations which are deeper. So let's look at.
I have a question from the other room.
Yes.
Can you flip back one slide? So essentially, you're saying a polynomial function is a linear combination of monomials.
Yes.
That's what you're saying, right?
Exactly. Yeah.
That doesn't need a proof.
Yeah. It's a fairly. The main idea of the proof is fairly simple, except that when you get into the details of what happens if you change this quadratic activation to a sigmoid or some other activation, and suddenly you start allowing the lower layer to be trained, then it is not that clear anymore. It gets much more.
I see, but that's not what you just said. Because you just said using the base, if we limit the base to be monomial, and then we do the simple linear combination, then we are guaranteed to recover the
polynomial. So I'm not
polynomial.
giving the exact final proof details. I'm just giving the main point of the proof here.
Okay.
So let's go to handle more complex nonlinear functions. Let's go to teacher networks that are deeper. Okay. So in the student-teacher framework, you have a teacher network that is a black box, but it is also a deep network, and you're given input-output pairs from that, and then you're training a student network to fit these input outputs. And it makes a lot of sense to study this framework because we often believe that real-world functions can be represented by using a deep network. So if you are trying to learn real world functions, then we better be able to learn a network that is capturing that function. So we'll just take a synthetic deep network here. Let's take a random deep network here, and let's try to check if it can be learned by using a student network. Let's even assume we know the shape of this network. Empirically, we did this experiment. We took a random deep network, varied its depth. We fixed the width to be about 100. And this is with ReLU and this is with sign activation. And we check how much the accuracy drops with the depth. So here's the awk loss. Okay, awk loss of 0.5 means basically you're not learning anything, because even a random prediction will give you an awk loss of 0.5. 1 means you're perfect. So notice that at very small depth, you have a very high accuracy. So you're really learning depth 2 networks quite well. And it kind of drops progressively as you increase the depth. By depth 14 or so, you basically almost know nothing about the function. So the function gets very hard to learn, at least using deep learning at these depths. So with these observations, we will next show that we can theoretically prove that for small depths, there is a reason why you can learn with pretty good accuracy. And we will argue that for larger depths, actually the learnability, not just using deep learning, but using any algorithm, should drop exponentially in the depth. So they are hopelessly hard to learn. And maybe they become cryptographically hard.
So the parameters of the network are chosen randomly.
Mm-hmm.
And both are the same shape, same shapes as.
We varied look at this. We varied the depth. We allowed it plus or minus 2. And we actually allowed the width also to double. And it doesn't make that much difference. So let's try to look at learning just teacher networks of depth 2 and see why this is easier. So you have a teacher network with weights W and a student network which is initialized with some random weights theta. And then you're doing gradient descent on the loss. And you're hoping that theta starts approaching W. It doesn't have to fully approach W. It can approach a permutation. Or maybe it doesn't match fully, but it just matches in the function value. And what we found is that there is a conceptual argument where you can actually map this dynamics of this gradient descent to a certain electrodynamics. That is, you look at these weights W coming into each hidden node. You can think of each Wi as a vector and each theta as a vector. For simplicity, just assume that these two are already the same. The top layer are not different. So then you can write these points, these Ws, think of them as points in a high dimensional space. And you can think of them as fixed protons, okay, which are fixed. And then you can think of the student networks, hidden weight vectors, call them thetas. You can think of them as electrons in space, in the same dimensional space. And as gradient descent is happening, essentially it's moving these electrons, which is the student network. It's moving these electrons. And the hope is that somehow it will match up with the permutation of the protons, which are the final desired weight vectors. And if you track the dynamics, it exactly matches this electrodynamics, where there is a certain potential function, where the electrons are getting repelled according to that potential function, and they're getting attracted to the protons according to that potential function. And eventually you want them to line up. And the reason why it matches the potential function is because if you look at the loss, you can write each function as some linear combination, because we are assuming the top thing is linear. So it is some linear combination of these sigmoids dotted with theta is minus Ws. So we expand it out, you will get a pairwise term for each electron, and you'll get a pairwise term for each electron proton. And so you will basically get some potential function for repulsion for electron minus potential function for electron proton. And the dynamics exactly match 1-to-1. Now, the potential function depends on the activation function. So this is not a standard potential function. The standard potential function in real life, in the real world in physics, is 1/r. And for this particular potential function, it is known that if you start with a set of positive charges, fix them, and you take a negative charges, and you allow them to move, they must actually eventually line up with in permutation. So it works for that. But that doesn't correspond to any real activation function. What we show is that there is some synthetic activation function for which the same property holds. And there are many other results for two-layer networks. There's one result for ReLU, which someone showed that this should hold up to some other assumptions. So that does it for two-layer networks. Now let's go to deeper networks. What we will argue is that as the network gets very deep, the function gets very hard to learn.
I have a question about the previous one. How important is it that you use quadratic laws?
In this analysis, it was quite important. I don't know how to
In practice, have you done experiments with different?
In practice, it seems to work. Oh, no, I've not done experiments without quadratics. So we will argue that very deep networks might be very hard. And here is the rough reason. It turns out that random deep networks are almost like random functions. They are almost like random hash functions. And here is the reason. If you take an input, essentially each layer is performing a rotation, a random rotation. And then it is doing some nonlinearity and doing that over and over. We will argue that as you do this successively, the outputs have basically no correlation with the input. In fact, let's take some correlated inputs, some two inputs that have a very small angle. And let's study what happens to the angle as you push it through this network. It can be shown that the angle will go on increasing. And over the different layers, eventually it will become almost orthogonal. You can theoretically prove that the expected dot product drops exponentially in the depth, which means they get completely uncorrelated. So, which means that if you take a bunch of correlated inputs and you push it through this network, eventually they become completely random looking uncorrelated.
Do you need linearities for that, or even linear stuff should work?
No, you need nonlinearity. If you just keep it linear, the angle won't change.
Rotation.
But we did similar things with a linear case, and it showed some complete decorrelation.
You write it out?
Yeah.
But can't you argue that a random Gaussian matrix?
But we did that thing called batch norm in the middle, but nothing else. But that's some kind of non-linearity. But
that sounds surprising because I feel that if you have a Gaussian random matrix,
so
you don't need to normalize it because it's already centered. If like everything is mean zero.
Yes, so it starts like this, and then like these two correlated mini batches become completely correlated. As your depth goes, similar kind of phenomenon.
The highlight is muted or?
Sorry?
Can you hear me?
Yes.
So I know this for a fact that in random matrix, this is one small branch in applied math. If you use IID Gaussian random matrix, you multiply to any vector. In mean average is equivalent to multiplying that vector with a Hermit orthogonal matrix.
Mm-hmm.
Sure.
And it's trivial to prove that concept. So here, when you say random deep network, so if each layer is an IID Gaussian random matrix, then it doesn't change the.
No, there's a
There's a nonlinearity. So I agree that if
that's
it's random IID.
Shankar was saying if there's no nonlinearity, then this angle would not change in average mean, not for each instance.
That's what I would think also. So I'm surprised. Maybe we should look at it.
Batch norm.
But they're already centered, right? If the Gaussian matrix is mean zero and everything.
Mean zero. No, I mean like the activations are being centered every time, right?
Yeah, but if there's no nonlinearity, if the Gaussian matrix is, if this is the input distribution is mean zero, then already things are mean zero.
It'll just be a rotation.
It's a good. We just did it empirically, and we saw this behavior, and we thought this might be some reason to explain why certain phenomena happen.
Oh, let's look at let's talk about it.
Were your inputs also centered already?
The inputs are around a ring. Yeah.
So I don't know what happens if you have a product of many normal matrices, because the spectrum, I don't know how it behaves. It may not be a rotation anymore. Maybe you're observing phenomenon like that.
Okay. But there's a collapse.
Yeah, but definitely with nonlinearity, the angle becomes closer to 90 degrees eventually. And you can use this to prove that it's statistical in the statistical query framework. It's hard to learn this problem below exponentially small in the depth. We don't prove cryptographic hardness, although it may be possible it's cryptographically hard. What we can show that if you take k inputs, then the outputs are kv independent of small k. For k about root n, we can prove that it's independent. What we would like to show is that it's true for polynomially large k, so that it's truly cryptographically hard. So this kind of indicates that a random deep network is not learnable, which means that the natural functions, if they're deep, they're probably not random deep networks. They probably have a much more structure to it, which makes them learnable. And the important question is, what is that structure?
Is there a mathematical definition for natural function?
No, natural function, I just mean the functions in real that we learn in real life. So our goal is to take natural functions and say that roughly it belongs to this class. It has properties from these classes of mathematical functions.
Well, you can argue that most physical phenomena are described by very low degrees polynomials, right? If you look at almost all theorems in physics, they involve fairly low degrees. I mean,
Well, but even a simple
turbulent flow and these kind of things that are high degrees,
but even a step function, right, is a very common thing in practice. Like suddenly you have an abrupt discontinuity, and that is quite high degree if you want to get a good approximation.
Well,
No, I don't know.
with like 5.
5.
Rational though. Rational.
You need a rational approach.
No, but like if then else, we do if then else processing in our mind, right? Once you get logic, well, that is so far from polynomial.
But the issue is this: if you look at the typical numerical partial differential solvers, they use piecewise polynomial. They're local, low-order polynomial. You piece them together as you refine the mesh, you get better and better accuracy. So here, when you talk about polynomial, you're only referring to the global polynomial.
Yeah, I'm not supporting any piecewise stuff here. Because by piecing things together, you can actually get very complex phenomena.
Right.
So here is one possible class of networks that might be more learnable. And these are networks which are more modular. That means you have a deep network, which could be very deep, but somehow there is a cut in the layer in the middle where you have a sparse cut. And what I mean by sparse cut is that the outputs of these are very sparse. So maybe the thresholds in the neurons below are so high that only a few of them are firing. In this case, we show some evidence that this teacher network can be learned by using divide and conquer. And what I mean by divide and conquer is that you can somehow first learn this lower layer, and once you've learned the lower layer, you can learn the upper layer. And why is it easier to learn the lower layer if you have such sparse cut? You can prove that if the thresholds in the lower layer are high, so that only a few of them are fired, then somehow this whole network has a high correlation with just this lower network with one layer on top. So even though this is very deep, approximately it is closer to something of depth this. Not exactly. So there is value being added in the upper one. But since it's approximately close to this one, you can apply, if you know how to solve a T/2 network learning, you can use that to get this one, and then you can build this on top. So maybe if our real world functions have a block structure, then maybe that is helping us stack layers upon each other. So let's now go to the more speculative part of the talk. And this is where I think I would like ideas that you guys may have. What should we do architecturally in deep learning to capture more difficult cognitive tasks like language and logic? Is the current deep learning framework enough for these things, or do we need to have radically different ideas? And let me tell you what will be nice. This is our current view of deep learning. Let's say you have a dog classifier. It looks like this physical network with just numbers flowing through. There is no interpretability here. The outputs are labels. And what we would really like is some kind of object-oriented view of the world where the output is not just that there is a dog present, but something like you have a dog class, object from a dog class, with attributes, like this is the breed, this is the size. And we would like to see functions here, functional or procedural view here, because in real life, when we are doing logic, we think of applying functions and procedures, and we don't see any functions or procedures here. And that is exactly what makes deep learning so not interpretable today. Not just that, we would also like that this classifier returns an object to dog, but we'd also like to point to related events. Like maybe you want to point it to the owner object who owns this dog, or some other events like you ran to a dog park and where you met the dog before. So we'd almost like to arrange these findings into some kind of a nice knowledge graph.
Great.
So how do we bridge from this physical view of the deep network to a conceptual view, which is like a functional view or object-oriented view? And I think that would be very useful for doing more advanced cognitive tasks. Another very important thing that I think that's very important is memory. So we make use of memory so so strongly in our day-to-day computations and predictions. And the basic question here is, when I have a complex input or a complex video or complex interaction, how do I represent that in memory? And how do I store it in memory? How do I link up these related events in memory? So if you just close your eyes now, you can even imagine the scene of this room. That means whatever representation you have in your memory for this room, it's actually reversible. That means you can reconstruct that. You can probably say that this is a table here, there are people here, this is roughly the number of people. You may not be able to reconstruct it exactly, but to some extent. And that construction is also fades away gracefully, in the sense that if I were to ask you tomorrow what is there in this room, you may not be able to reconstruct it with the same level of accuracy, but you'll be able to reconstruct it approximately. So even if you stare down bits in your sketch representation of this object, it gracefully degrades. And also, how does this memory interact with the actual computation of inference computation? And I think memory probably also goes well with this modularity. That means you don't want to have this one black box end-to-end network, but you probably learn tasks over time. So you learn simpler tasks. When you're learning a language, you learn very simple phrases, and you build a module. Perhaps you learn a module and tighten it for learning simple phrases. And then you learn complex interactions between the phrases. And then over time, you learn the niceties of that language. So I believe that, and I would like to get your opinion, whether you think it's the right direction to go from this end-to-end fixed architecture to something where you are growing a class of functions that are building on top of each other and interacting with the sketch memory. And one advantage of this module is that these modules could be returning not just a class, not just a label, but also attributes. Like you found a dog and the other attributes of the dog. So you can think of these modules as a function that returns a class object. Further, the modules may be heterogeneous. Today, we just have one single module that is learned end-to-end by deep learning. Here, we can have heterogeneous modules where some of them are based on logic. They are done by using predicate logic and proof resolution, refutation. So we don't have to have just one tool. You could have some discrete algorithms. You could have some other optimization frameworks. You could have EM algorithms. So different modules could use different algorithms. And further, modules may evolve over time. So you may add new modules. As you learn a new concept, tomorrow you find that I'm learning this I'm seeing these new things, and I find that there's some commonality across them. So I could allocate a new module and then learn it over time using the best possible algorithm. So here is one proposal for how to represent complex phenomena and how to store it in memory. So let's say we are just having this meeting. Like in the end, I want to say that there is some representation or sketch of this meeting that we'll store in our minds. So for that, I will assume that the network is modular. Okay, I'm not telling you how we take today's networks and make them modular, but I'm just assuming that the network already has some number of modules. Like maybe to detect a human, we have the lowest layer, we have modules to detect edges and curves and color, and then the upper layer we have which takes these inputs and detects basic shapes, and then we have components like eyes, hair, nose, and then we have something which can detect a human head, eventually a human, and maybe the eye can also detect animals. So we'll assume that you have such a modular network, and such architectures have been proposed, as I said, by other people as well. But the question is, even if you have such a modular network and you have a complex input here, let's say the image of a human, how would you store that human or that image in your memory? You probably don't want to store that raw bitmap because the raw bitmap has no information, useful information per se, and it's also very big. So perhaps what we want to do is we just want to give that complex input and feed it to the network and see what is coming out of that input. What are the main findings? And if we want to store the summary of those findings. So we want a sketch of that input, let's say it's this meeting. We want a final sketch of this meeting, which tells you the essential attributes of this object. And it should be such that it should be somewhat reversible. That means if I give you the sketch of that object, from there you should be able to approximately reconstruct at least the main components of that input. So it should also be indexable, so that tomorrow, if there is another meeting with a related topic, it is somehow similar to today's meeting, and you can point to it and retrieve related objects. So it should be similarity preserving. So the sketch mechanism we propose is recursive. And I say recursive because when you store a person, you probably say that he has this kind of face and this kind of dress and this kind of, and what is the face? The face itself has these kind of eyes. So it's recursive. You can go drill down finer and finer details. So the sketch eventually, so these modules are outputting certain objects. And let's say these outputs can have attributes also. So you want to essentially summarize this computation recursively so that you know roughly what the input was and how it came to be this output. So even if there are lots and lots of modules in your network, but only a few of them fire, then a small sketch can be used to keep the essential combination of all these firings. And the main technique we will use is basically random subspace embeddings using random rotations. Here's the basic idea. Okay, you want to essentially encode the outputs of all these modules together when you sketch the final human that you saw here. And how do you do that? You just use a simple linear combination. Let's assume for a moment that all these modules are not arranged in a hierarchy, but they are all just flat. So you have a network, you have just a collection of modules, one layer, and only a few of them are firing, let's say. So how would you sketch the outputs of these few modules in a way so that given the sketch, I can tell exactly what are the outputs, what are the inputs. So this is the simple subspace embedding. You keep a random rotation matrix for each module, and you take the output of each module, and only a few of these outputs are non-zero. Most of them are zero. You just take this linear combination, just rotate each module output, rotate by random matrix, and add them up. And that is your final sketch. And I claim that this final sketch is a very good representation of the modules which fired and their outputs, because if the number of modules which fired is small and the sparsity is small enough, then by using dictionary learning techniques, you can actually tell exactly which module fired and what the input values were, as long as the total sparsity of these x's here is less than the dimensionality of the sketch. Okay, any questions?
So here the random rotation matrix Ri, what's the definition of Ri?
Yeah, it's just a random, let's say it's just a random Gaussian matrix. So think of xi's are sparse. In fact, most of the xi's are zero, and whichever xi's are non-zero, they are also sparse. So I claim that you are basically embedding each xi in some direction. So Ri represents a rotation. So you're taking, let's say this is a tiger module. So you're taking a tiger and putting it in the tiger direction. And you're taking a table module, putting it in the table direction. So when you get the final sketch, all you need to do is look at the table direction, the tiger direction, and see what is the value there. And you'll understand that there's a tiger in this image, or the table in this image. So it's a convenient way of packaging your information and the type information into your final sketch.
So do you require orthogonality different?
We require near orthogonality. Don't need full orthogonality.
So I can see the sparse coding connection. What's the dictionary learning connection here?
Yeah, so I'll tell you that here. So dictionary learning is the case where each Ri is just 0 or 1. It's just a scalar. So if I take a sparse combination of vectors here, then, and I take many such sketches, then it's exactly dictionary learning because these xi's are the atoms and you take different linear combinations of these.
Mm-hmm.
So in that case, it becomes exactly dictionary learning. This is basically a generalization of dictionary learning to encoding vectors instead of bits. Okay. And
so
this is, yeah.
So you're saying that the outputs of the modules are the dictionary.
Oh, sorry, I made a mistake. The outputs are vectors and these Ri's are bits. So Ri's are 0 or 1, okay? And no, wait. The xi's are bits and the Ri's are just vectors. Okay, I've made the matrices, but let's say Ri's vectors and the outputs are bits. And if only a few of the modules are firing, you take a sparse combination of vectors, and that's exactly dictionary learning. If you have many such sparse combinations, why? So if I give you many such sketches, I don't even need to know these vectors, these Ri vectors, and I can still recover them by the dictionary process.
Can you recover them if is there a upper bound on the number of non-zeros in the?
Oh, absolutely, yes.
Yeah.
You can recover only if the dimensionality of y is more than the total sparsity of all the xi's. Information quite clear. Yeah.
You need one sketch or many sketches?
No, if you have one sketch whose total number of bits is more than the essential number of attributes in the total models that are firing, then you can recover it. There's also a weighted version of this, where if you weight things differently, then you will not be able to recover those ones which have low weight. But anyone which has high enough weight so that it weights multiplied by the number of bits in it is sufficient, or that weight, that proportion of the sketch. If there's enough capacity there to encode this one, then you can get it. So you can get the top elements, you get the top weighted module firings.
Wait, sorry, you're storing all the RIs? Or
Actually, wait, that's a good question. So these capital RIs are fixed and random. There are two possible statements you can make. One is if you know these RIs, then if you're given yi, you can tell exactly which xi.
Yeah.
Okay, that is just sparse recovery.
Yeah.
But in fact, there's another statement you can make that even if you don't know these RIs, but you have lots of such YIs over different firings for different modules, you don't even need to know the RIs. You can apply dictionary learning to figure out which are these rotation matrices, and then just recover the whole framework,
Okay.
the whole thing.
So you could recover both the RIs and the XIs
If you have lots of
with many
Yeah.
Ys.
Yeah.
Okay.
So that's why you can actually recover their modules. So this is for one layer of modules, all in one layer. If you have a hierarchy, then you can actually, there's a small twist of this where you make it recursive. So when you take the vector encoding of a module, you don't just take the output of that module, but you also add some linear, with some weight, you add the inputs of that module. So that way, that thing encodes its inputs as well. So once you make it recursive, then not only can you, if you see many such vectors, not only can you recover the modules matrices, but you can also check how the modules are connected to each other. Because
So
the sketch.
there's no nonlinearity in this case?
No, this is not affecting the forward computation. The forward computation is going on as before. In the deep network is still computing as before. We are just appending some sketches. This is just the flow of the sketches. And that sketch is what we'll store in the sketch memory. In the memory. It doesn't mean that the forward computation will still go as before.
Okay.
This looks like some generalization of resident or shortcut type stuff. Do you think like that? Where certain activations are being propagated further up. And if you combine them in some random fashion, you can recover outputs at intermediate.
It could be, but I'm not really, this is not really doing anything to the network computation really. It's just doing something on the side.
Right. Okay. The reason I was thinking was if you have some representation of intermediate activations, you could think of recovering some intermediate depth by your earlier result, and then getting the entire depth overall.
Could be, yeah. So once you make it recursive, you can recover some of the parent-child module connections. And if you have enough things, you can actually recover the whole network. And one important thing to note is you are encoding the type information in the direction, which means you don't have to have this complex protocols as to how class structures are encoded. You don't need to have this, there's so many bytes for int or so many bytes for this, which is what you use in object-oriented programming language construct. So this gives you a protocol-independent way of packing types and communication across modules. So finally, it gives you a sketch for complex objects. Like even if you have this meeting, once you have a module that fires a meeting, by going recursively through that computation and sketching it, you can have a short representation for this meeting. And that short representation might not be enough to reconstruct the whole meeting, but it might give you the high-level attributes. Furthermore, if you have sketches for the lower-level phenomena, then they could point to those lower-level sketches. So having a hierarchy of sketches that way could be useful to getting the entire meeting details. So finally, you get a sketch representation for all complex objects. Like let's say you saw a person, you have a sketch representation for that. You have another person. Maybe all the people are pretty much very close to each other or in the same subspace. You can have sketches for topics of discussion. Maybe you have a meeting with the person X on a topic Y. So this thing will be very close to both. It'll have similarity with both the containing person X and the contained topic Y. You could have sketches for animals, furniture, works. Another important thing is that this could be useful for finding new concepts. Like let's say you see an animal, some person has not seen a tiger at all before, and he sees a few tigers. So the tiger will have some sketch representation in terms of the outputs of the lower modules, like maybe this is the eye type, and this is the body type, shape, etc. And we'll create a new sketch vector in some direction. And as if you see a few tigers, you'll see that they all kind of cluster. They form a small subcluster in the animal subspace. So that would inform that person that, look, maybe it's time to learn a new concept. So you'll allocate a new module And maybe to begin with, you will allocate a very simple module. You just do a simple, say, anything in the ball around the center is a tiger, or a simple hyperplane separating that cluster is a tiger. And over time, you can learn a deep module for that cluster, for the tiger, which means that you'll start learning very fine features of the tiger. So this is how you could potentially evolve your library of modules. And this could lead to a whole sketch repository of collection of sketches, which implicitly forms a knowledge graph, along with a modular network that is directly interacting with this one. The knowledge graph is implicit. Why? Because our sketch mechanism guarantees that if two objects are related, then they have a quite high correlation. So this meeting will have a high correlation with the topic of the meeting or the people involved in the meeting. So you get this implicit knowledge graph. And it could be used for retrieving related objects. If you're dealing with some object, you found some object here, you could retrieve from the sketch memory similar related object that and send it to some upstream module.
I have a question.
Yes.
Can you flip 2 slides back? So here you're saying the cluster or subspace, they're sort of equivalent concept in this sketch idea?
Yeah, I'm losing the word clusters a little fuzzily. I'm saying either related things could all be a small cluster, or maybe they are all in one subspace.
And the subspace you're talking about, is that the subspace spanned by the vector of xi?
Yeah, you can think of it as the rotation matrix R multiplied by xi. If xi is sparse, then this will all lie in some subspace.
But if the matrix Ri is n by n,
you're right, actually. So think of the case when xi has only the top few bits as non-zero and the remaining bits are 0. So in that case, effectively, Ri becomes rectangular. So if it's sparse in that way, like if x is sparse in a way where only certain entries are non-zero,
right,
then it falls in a subspace.
Oh, okay, then, but your subspace dimension is limited by the size of matrix Ri. If it's n by n, the dimension is n, is fixed.
Yeah,
and you can only squeeze so much into that dimension n.
Yes, but if if xi's have a smaller dimension than n, then the R will define some subspace where R times xi is present. So all furnitures will lie in some subspace. All tigers will lie in some subspace.
So the subspace, the R is the subspace invariance. It only projects to the.
Yeah, essentially. Yeah. Here are some provable properties that you can theoretically prove. So we were talking about learnability in the first half. And what we can prove is if you have a modular network. Now, the modular network is deep, and there's no guarantee that you take a deep network, it can be learned as a teacher network. But we prove that if you take inputs, output pairs, and you augment the sketch along with output label, then suddenly the network becomes much more learnable. In fact, we can prove that's learnable under some assumption.
Not random networks, or still random?
No, not random. And there's a specific reason for this, because the sketch essentially is not just telling you the output, but it's telling you the rough pathways by which you got the output. It may not show the entire pathway, but some condensation of it. So over many different computations, you can get sort of the connections between the modules.
So if you learn some new modules, does the previous sketch remain unchanged, or you have to change them?
Well, I don't know how you would do it in real life, right? So if I learn tomorrow that there's a tiger, I saw a tiger tomorrow. Maybe when I learned that there's a tiger, I revisit old things in my sketch memory which were related to that, and you correct them. Say, yeah, now I realize that those old things are also tigers. So go in the sketch memory, you rewrite them using the new sketch module outputs. You rewrite those sketches. It also makes it more interpretable, as I said, because you show how the label comes out. It has graceful erasure, because if you're applying this random rotation, the subspace embedding, even if I drop some of the bits, there's enough bits that I can recover the things, at least the high level things. And even if there are too many things being packed into that sketch, you may not get all the attributes of all the different components, but you might get the high level ones. There should be high weight ones. You can also prove that you can get simple statistics, like if you have a sketch of a room with some number of people, you can get roughly how many people are there, what is the mean properties of these people. It is similarity preserving, as I said, which gives us knowledge graph. It gives type information and high-level object-oriented information in a protocol-independent fashion without having a agreed upon a compiler interpretation. It can be used to act as pointers because if a sketch is packing too many things, even though you cannot recover all the things, you could use this as a reference and you can index into a more detailed sketch. It helps to detect new clusters. Another thing I want to point out is floating modules. So far, modules were hardwired in a specific architecture, but it is useful to think about floating modules which are not necessarily tied to any incoming modules, but they are more like generic functions and procedures. And here are some examples of floating modules. Think about a counting unit. Okay, this is just counting repetitions in an image. You can also have counting of how many times I hear this sound, or just more higher level counting. Like I'm thinking about something and something happened 3 times, then I want to apply the counting unit there. This is a unit that will be applied at very different levels of abstraction. It helps to make this a floating procedure. You can have a clustering unit where you could be clustering images, sounds, higher level thoughts. You can have a curve analyzer where you're just given a visual curve and you're trying to capture the curve using a few coefficients of a polynomial or Fourier coefficients. But this is not just for describing curves on a whiteboard, but also for curves about how some sound is changing. Or perhaps this is taking a sketch representation of a video. You're taking frame by frame. And the sketch can actually take an image and put it in a point. So as the video is evolving, it actually gives a curve in a high dimensional space. So such a thing could be applied at a very high level, much higher levels of abstraction. I'll argue why this curve representation, this curve analyzer is potentially a very useful component for complex cognitive tasks. Think about a video of a person walking or a snake slithering on the ground or a butterfly flipping its wings. Okay? How do we recognize that this is a person walking, this is a snake slithering, this is a butterfly? So this is a video, we are looking at this images frame by frame. And each frame will give you, so notice that this video is periodic. Because if you just focus on this person walking, it'll just keep moving it. Unless you're tracking the eyes with the person, so you just keep shaking this. And this is also periodic if you track the eyes. These are periodic videos. The sketching of each image will produce a point in sketch space. And the video is periodic, so it'll loop. It'll produce a loop in sketch space. So this is one loop in the sketch space. This is in another loop. It'll have this will mostly be in the butterfly subspace, in the person subspace, this is in the snake subspace. So essentially, to tell that this is the video of a person walking, you just need to figure out what is this loop representing. So if you have a curve classifier, which could take that loop and tell you that these are the coefficients of the loop, and this is roughly the orientation of the loop, then a good curve classifier could actually tell you that this is exactly a person walking, the snake slithering. And that's why if you think about this in a modular way, with sketch representation and curve analyzer, with floating modules, it will be quite beneficial. It could also be applied to language. When we see a video, a complex video, and we try to use language, what did you see in the video? That you saw a dog running and jumping over a fence. Again, this is just a curve in a sketch space. So language, perhaps one view is that parts of language are trying to express a very complex curve and express that in words. So think about just a ball moving in space. A ball moving in space, if it's continuously moving, you can just describe it using the coefficients. But if it's bouncing around, you want to say something like, okay, now it bounced with this angle, and now it's if it's bouncing back and forth, so you're going to say that it's iteratively having this periodic motion. So the moment you get into this expressing things, it already becomes rich structures of language. So just to conclude, I would love to discuss what you guys think are the best ways to conceptually start thinking about these complex cognitive tasks. Do you need to add new architectural changes to deep learning framework? And here are the references. You can go/theory of learnability. That's it.